Okay, so let's start for the second day. So what I'm going to do is I'm going to start our studio like I did yesterday. And then I'm going to reopen the project that I created yesterday so that I have direct access to all the files and directories that I created. And R uses the same working directory as this. So to do that, you can click on File, Open Project, or even probably recent projects. Here, yes. And as far as I can remember, I call my project R intro. Or if I'm not sure which project it was, I can click on Open Project, and then navigate to that project directory, and then select the R proj file. That's the file that defines the project, and click Open. And our studio is going to restart its R session and set the working directory in here in this directory that I created yesterday. So one thing that we forgot to do yesterday is to, or maybe you have done it, to download the data that we need for this course. So there is an intro.zip file on Google Drive, but you can also download that archive from the course web page and the URL. What is the URL? Here, so this is the URL. To write it down for you. So here at the top of the landing page, you can download this rintro.zip file, which I'm going to do now. And again, there is a PDF version of the lecture notes that you can also download here. And it's probably available, although slightly outdated now, in Google Drive. So what I'm going to ask you is to get this our intro zip file with all the data. It's downloaded here twice if you need that. And then take all that data and copy it in this directory, in the data directory in our project. So that's where we will have the data that we're going to use today. Here. that now I have in my project directory, data, and in data I have all these data files. Okay, so once you have done this, could you put your green or blue sticky notes up so that we can then proceed with today's material. And so in the meantime, I'll summarize the main points that we have seen yesterday. Yesterday we have learned about variables and about factors, which is the first data structure, maybe most basic but most important data structure in R. So we can represent factors like this. These are linear elements, linear data structures, and they're composed of a certain set of elements. First one, the second one, and so on. The last one, the index of the last one. So imagine that this vector is stored in a variable called x. The index of our last element is length x. And so what we have also seen, we have seen different types, different classes of vectors. We have seen numbers, and in R they are called numerics. We also have seen that they can contain characters, and they are called characters in R. And we have seen the third type of vectors, which are logicals. And logicals are either true, or capitals, or false. We have also seen that we can subset vectors with square bracket operator. And inside here, we can either use indices, or we have also seen that we cannot use logicals to do the subsetting. And one particularly important example of subsetting with logicals was the following one. So I'm going to reopen the S01 start R script that I created. So here is a record of everything that we did yesterday. So I can here recreate here, this vector, and then I can make this logical questions about each specific or each individual element of my peptide. Which of these elements are greater than 10, or which of these elements are smaller or equal than 20? And so this generates a vector of logicals of this specific length that I can then reuse immediately within my square brackets to do my subsetting. Okay, so these are concepts that we're going to review today, but not on vectors, on kind of bigger data structure that are probably much closer to the kind of data that you would analyze if you have, for example, quantitative proteomics data. Yes?
So, I mean, I've coded with other different type of languages. That just seems to me like a simpler way of doing conditional statements. I don't know if you know what I mean by that.
I do know what you mean.
Like, it doesn't seem like we need the if and else statements there. So, like, for me, it might be a little bit more like harder for me like to work with. So, can I still add the if conditional statements there?
You don't need to.
I don't need to.
No. If conditions exist in R, when you want to write a program, you can use them. Of course, if condition, else condition. But here, this is not meant to. You can always a programming language, but here we are using it as an environment to explore data. We don't want to write 10 lines of code to say, well, if this element is greater than 10, return true. If it's not, return else, return false.
Yeah.
We want concise syntax to be able to easily express these queries that we have about data without having to program it. Under the hood, if we look at the code, there is code behind the square bracket operator, count behind the great arrows, all that signs. And of course, if we look into the implementation of these, there are conditions and if-else. But here, this syntax is meant to be used interactively to explore data.
Okay.
So I'm going to create a second script file here, file, new file, and R script. And I'm going to call S02, as I started yesterday with an S01, and I'm going to call it S02 data frame. And we're going to see in a minute why I want to call this data frame. And then I'll finish my file with its extension, which is R, capital R, lowercase r, but I started with capital R yesterday, so I'm going to stick with it for the rest of the worksheet. So this S02 file is the file that I'm going to use for at least half of today. And by the way, if you want, what I can do maybe over lunch or certainly at the end of the workshop is to save my R project. When I say saving the R project, it would be saving the directory that contains all these files and directories and share it with you. So all the code that I write, all these scripts that I write, you have access to it. So yeah, I can do that. Okay, so the first function that we're going to see, and we're going to use it without much explanations, and then we'll go into the details later on, is a function read.csv that, as its name implies, is going to read data that is stored in the CSV file. So are you all familiar with CSV files? CSV stands for comma separated value. Would anyone want me to describe a little bit what the CSV file is? Yes, okay. So, well, we can have a look here in the data directory, probably here, and we have a set of CSV files and other files, and we're going to see later what these are. And in particular, this IPRG example one summary CSV file, which is the example data set that we're going to start with. So I'm going to try to open it, but not open it with, for example, Excel, but open it with a text editor. And so if we look inside this file, what we have is the following. We have a set of lines, and each of these lines correspond to a line in a spreadsheet. And then each of the columns in our spreadsheet are defined here by a set of commas. Okay. So on each line, the first word, if you want, before the comma will be represented as the elements of the first column in our spreadsheet. And then everything between the first and the second column defines the second column in the spreadsheet. So this is how the data is encoded as a plain text file with commas separating the different values. I assume that if I double click on this, it's probably going to be opened by default, yes, by Excel, and Excel will automatically recognize that this is a CSV file and automatically parse it like this. So indeed, the first line here is a header, These are titles for respective columns. And here we have a protein, a Swiss port identifier, an intensity, a run identifier, a condition, and so on. Identifier, condition. And if we look at the CSV file, we see exactly the same information. The first line is a header, separated by commas. Second line is the first line of data, again separated by commas. So this is a CSV file. You could replace all the commas by tabs, and then you would have a tab separated over TSV file, and so on. And so these text-based spreadsheets are commonly used to exchange tabular data between different software. The XLS or XLSX format is something that is specific to Excel, although it can be read by other spreadsheet software. CSV file is kind of a universal way of storing tabular data. That can be read into R, into Python, and many other programming languages. Having said that, it's also possible to read Excel files into R, but we're going to focus on CSV files. Okay, so we are going to use this function read.csv, and we are going to give it the path to these IPRG run summary file. So the path to the file is a character, so we must absolutely quote the input to read.csv, and this file IPRG example run summary.csv is in this data directory. So I have to specify data / and then the name of the file. And then before running this function, I'm going to create or to store the output of the function into a new variable called IPRG. So I'm going to execute this line of code, and nothing apparently happens, at least nothing on screen. It reads this data, it doesn't complain, so that means reading that CSV file was successful, and indeed we can see that we have a new variable that appeared here in our environment. So if I now look at the class of this variable, class of IPRG, it tells me it's a data frame. So a data frame is the R equivalent of a spreadsheet, if you want. So could I just have a show of sticky notes if you manage to read that file into a variable called IPRG, for example, or something else, and if not, we're going to come and help you finish this. And you can use auto-completion. So if you start to type read.csv, opening parentheses, opening quote, and you start to type data, you can use the tab and assume that you have the data directory in your working directory. It will autocomplete the data, and then you start typing IPRG tab, it will autocomplete the file name, assuming that you have that file name in the data directory. So, what is a data frame? It's the equivalent of a spreadsheet in Excel, but with additional constraints. So I'm going to first show you how one should not store data in Excel. well, at least if you plan to load that data into any data analysis software, you should absolutely avoid to store your data in something like this. Okay, so this is a screenshot from an Excel spreadsheet, so that's a particularly horrible offender. That's an example of how not to use spreadsheets. Okay, so for example, this one spreadsheet has been used to store 8 different subtables. And even though it might be useful as a user to have an overview of these kind of 8 different surveys, these 8 different subtables, this is not something that a computer can read. In addition to the fact that we have 8 different tables, we also have some annotations on the side. Again, this might be something that is very useful as a user to see, some average and variability within the subtables. But again, if this is exported to a CSV file, the first row will contain 1 T1, 1, 1, 2, T1, 2.6, 0.59. So there is absolutely no structure in this table. So if you have a table like this, you stand no chance to read it into R, but it's true for any data analysis software. You will actually, it's just not going to work. Even with advanced programming skills, you'll waste days and days and days trying to reformat it. So how should a tabular data look like for it to be easy to import in R, and after that, easy to analyze? Well, it should be a perfect rectangle. Well, it could also be square, it could be a white rectangle. But there shouldn't be any piece of information hanging out, sticking out to the side. Like, for example, little annotations like these. Okay? So it has to be a well-formatted rectangle. So this rectangle is composed of a set of columns and a set of rows. And there can be many, many rows and many, many columns. Along the rows, we typically store observations. And along the columns, we store some variables, some piece of information that we have recorded for these observations. So let me write here observations and variables. So if we stick to this rule, we can start to do some reasoning on our data set. But first, if we strictly stick to these rules, every cell will contain one and only one piece of information. So let me show you another spreadsheet that is maybe not as bad, but violates this rule that every cell should contain one and only one piece of information. A small table about a kind of collection of animals in a survey, the date when it was collected, what plot that species was found, its weight, and then here we have a column where we have 2 pieces of information, 2 columns that are stored inside the same variable. The species and the sex of that species. Okay? So this is problematic. It's not impossible to fix, but if your data look like this, to fix this data, you would need to know some extra functions, whether it's in R, in Python, or in Excel, that's going to say, well, take each cell here, separate it, or take the value, split it based on the dash, and then everything that is on the left of the dash becomes the species, and everything that is on the right hand side of the dash becomes the sex. Okay? So it's not too difficult to do if you know the command. I know how to do it in R. I don't know how we do it in Excel. And you probably know how to do it in Excel, but you don't know how to do it in R. So the easiest thing to do is to start with a properly formatted data table and avoid having multiple pieces of information within the same cell. Okay. So we have observations along the rows and variables along the columns. If we stick to this rule, every cell contains only one piece of information. Now we can now start to do some reasoning on this data. For example, if I take this cell here, I know that it contains information about my second observation. And exactly what observation? Well, the value for my third variable. Similarly, if I take this cell, it will be the same piece of information, the value for the same variable, but for another observation. I can take any line of this data frame, of this table, without actually looking at the data frame, looking at the data, and there is no data, I just made it up, okay? But if I stick to these conventions, I can take any line, and I know that this is a record of all the of all the variables for that observation. And if I take any other line, I know that I have exactly the same set of variables for another observation. Yes?
Would it be critical if we kind of change variables and observations? The variables would be in the lines, because for example, if we have like proteins and replicates, then the observations would be proteins, right? Or replicate. Is it free or is it other like?
So we're going to, for the type of data analysis that we're going to go into late in the afternoon, typically you have your observations along the rows and your variables along the columns. Now, your observations could be different proteins, and then variables that you have is an intensity, but then you could have intensities in different samples. I'm going to come back to how to encode it. So that's one way of encoding data, and that way of encoding data is called tidy data. That kind of data is called tidy. It's clean, whereas something like this or something like that is very, very messy. And the messiness stops us from doing data analysis or visualization. And really what stops us from analyzing that data or visualizing that data, it's that we cannot reason. And we need to be able to reason on data to be able to analyze it, okay, to transform it, to take some information of interest out of the data. So for example, let's assume that this column here is some sort of intensity that was measured, maybe peptide intensities. Well, if I want to look at all the intensities or the distribution of intensities, it becomes straightforward. I extract that column, and that column gives me all the intensities of interest in that data. So that's the kind of reasoning, the kind of subsetting that we will need to be able to do easily and quickly to proceed with our data analysis. And so, based on the questions you had, very often in omics data analysis, proteomics in particular, we have these kind of tables where we have our different proteins here and then samples. Samples 1 to P, proteins 1 to F. Very often we have a table like that. Strictly speaking, it's not that kind of format, but depending on what kind of analysis, what kind of visualization you want to do, these this structure might be more useful, and depending what we want to do, this structure might be a better fit. But it's important to have this notion that whether it's this tidy data or this white data, they are still structured. And we know exactly that if we take one column here, we get all the intensity of one sample, or if we take one row, we will have that protein and all the intensities across all the samples. So we have now read this data into R, and let's start to explore it, see a little bit what we can do with this data. So one function that is very useful, very important, is the dim function, and the dim function returns the number of dimensions. Oh, let me say one more thing here. Before we saw what vectors were. Okay? Linear objects that had a length, and they had a single dimension, and this single dimension was the length of the vector. Now we are starting to work with two-dimensional objects, and these two-dimensional objects have dimensions. Let me clear my screen and show this at the top. And dimensions, these two dimensions are on one hand side the number of columns, IPRG, and the number of rows of IPRG. So I have 7 columns, that means 7 variables that are encoded in this data set, and 36,321 rows. So 7 variables that have been recorded for 36,000 and so rows. And the dimensions of such an object is always first the number of rows and then the number of columns. Okay, dimensions returns 2 values. So dimensions returns dim. The dim functions returns a vector of numbers of length 2, and the first length corresponds to the number of rows, and the second one corresponds to the number of columns. And so how can we relate what we have seen yesterday, the concept of vector, to a data frame? Well, every column of this data frame is a vector. So if we ask about the call names of IPRG, here they are. So we have 7 column names. We had a header and 7 columns. And the first one is protein here. Well, in this data frame, we have 7 vectors. The first vector is protein, the second one is log2 intensity, run, condition, and so on. And each of these vectors have, by definition, the same length, because they are all part of one data frame. And the data frame is a perfect rectangle. We do not have any bits that stick out. So whenever you read data in, it's always good to have a quick look at it to make sure it looks right. And 2 places of interest to look at a data set to make sure it looks right are its head and its tail. So the head function returns the 6 first observations of this data frame. So rows 1 to 6, that corresponds to these proteins, these intensities, and so on. And the tail returns the 6 last observations, and indeed the last index here is the 6, 3, 2, 1. Okay, so if read.csv did not complain, that's a good sign, but it's always good to have a quick look at the top, at the bottom observations. There is actually, if we use RStudio, another very useful function that is view with a capital V, and that in RStudio we automatically fire up this spreadsheet editor, although you can't change it, but you can then also quickly visualize your data as you are used to interact.
Could you please repeat all?
Pardon?
Could you repeat all?
Yes, let me switch back to my script file. So it's view with a capital V. But it's still useful to know head and tail. Head and tail will also work with vectors, and they are not. You don't need to use RStudio to use head and tail. Yes.
Is there any way to change that function to read top 10?
Yes. There is. And how do we find out? By looking at the documentation. And if we look at the documentation, we see that head here has two arguments. The first one is x, that's the variable that we want to look at. And then afterwards we have an n that by default is 6. So if we wanted to look at the 10 first, we could then say head 10, and then we would see the 10 first rows. And two other useful functions to explore objects or variables in general are str, that stands for structure, that shows us a summary or the structure of this object. It tells us it's this data frame with that many observations. Observations correspond to rows. That many variables. Variables correspond to columns. And then here we have protein of 2 intensity and so on. And it tells us that these are numbers or factors. We'll see the factors later, but these look like characters. We'll see into more details later on what they are. Oh, and maybe a last one that is also useful is the summary function. The summary function will basically call this summary on each variable, and so it will basically count for each. So it will take the first column and then count how many of these, how many times this protein identifier occurs, 12 times. A summary of this numerical value, it will tell me that the summary statistics, the minimum, first quantile, median, mean, third quantile, maximum for this intensity is this, log 2 intensity, and so on. So it gives a kind of numerical summary of the data frame, or each individual variable of the data frame. Yes?
I've actually noticed something. So when you do the tails function and you compare the numbers with the view function, it gives you like a rounded number code.
Okay.
I don't know if you know, this is the tails function.
Yeah.
Maybe this is the view function, this is the tails function.
Tail or hat will be the same. So here the intensity, we don't have a decimal number, but if we look at it here, okay, I don't see them here. So you have decimal values? You see decimals here?
Yeah, I see decimals on mine.
Okay. So it's very possible that. So what about the other people? Do you see decimal numbers? So here, look, 2 intensities, yes, but not in my intensities. So you have decimal numbers in your intensities?
Yeah.
You too? Okay, so there might be differences in the RStudio versions. They might display the decimals. Let's see. No, I'm not going to do that now because I will use syntax that we're about to see. So, assuming that we all use the same, that we wrap the same file in, the data that we have will be the same. It's possible that it's displayed differently to save space, for example.
But if this was to ever occur, where will our research in R, would it be accurate to our data, or would it be rounded?
No. The values that we have now in R are as accurate as the values that were originally in your CSV file. If you worry about the accuracy of your values, then you should be worried about what you have in your CSV file, which is probably has been rounded when it was exported to CSV file. R has all the precision that you need for all your computations. Or another way of saying is that the limitations that R would have are based on how computers are built, and these are the same limitations that any other programming language has. Okay? So we have seen yesterday that we use the square bracket operator to subset vectors, and we can do the same thing to subset data frames. And yesterday there was a question, I think, when we had this command. Somebody suggested that, well, maybe instead of the and here we could use a comma. And the reason why this is not possible is because the comma is meant for something else. The comma is meant to subset two-dimensional objects, like data frames. So everything that comes before the comma refers to the first dimension of this object, which is the rows, and everything that comes after the comma, but always within the square bracket operator, refers to the second dimension of that object, which are the columns. So for example, if I wanted the first 10 observation for the 3 first variables, do you remember 1:3 will automatically generate a sequence 1, 2, 3, 1:10 will automatically generate a sequence 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I wanted to kind of the upper left corner of this data frame, I could specify it like this, where I have 10 first observations for the 3 first variables. So the same concept that we have seen yesterday, square bracket operator, and we can use indices to do the subsetting. We'll see later that we can also use logicals, but subsetting along the first or the second dimension. If we omit completely a set of indices before or after the comma, that means all observations or all variables along this dimension. So this tells me to have the 10 first observations and return all the values, all the variables, and this would say all observations but only the 3 first variables. So we have seen with the names or call names, they will provide the same result, that our variables are named from the original header in the CSV file. And this means that for the subsetting, we can use indices, but we can also use the name of these variables. For example, if I'm interested in the variable run, but I'm not sure which one it is, so in this case it's the third one, but this might change when I manipulate my data, I can also use the name of an observation, or in this case of a variable, to extract all the values. So the values for that variable for all my observations. So using names is very, very useful and avoids mistakes where, for example, I want run, but instead of using 3 here, I would use 4 or anything else. Another way to do exactly the same thing, and that saves a little bit of typing, is to use a new cryptic character, which is the dollar operator. Dollar means go and get that column in this data frame. And then with the dollar, I can use auto-completion to extract, again, variable run from data frame IPRG. So let me complete these 3 possibilities here. So these 3 will do exactly the same, assuming that run is my third column. 3 will do exactly the same. The first one is the most dangerous one because we assume that RON is the third variable. The second one is really good because if we want RON, we are sure that that's what we get. And the third option here is the easiest to type because after the DORA we can use tab completion. Okay, so here we could always, assuming I'm not careful, and instead of U I type I press I, that is just next to the U, I would get an error here, okay, telling me that if there is an undefined column selected, right? But here, with the tab completion, I see I can use tab to autocomplete, so save me some typing and save me some typos. Yes?
If we want to select several columns, do we have to use the...
Very good question. So if we are interested in, so let me check the names again. So let's say we are interested in RON and intensity. So we could see that RON is the third one, intensity is the sixth one. So we could type 3, 6. But we could also create a vector of names where we spell out that we want column RON and we spell out that we want column intensity. So this is a little bit more typing, but again, we know what we get. So I have a little exercise for you now. I'm going to leave this a second while I do this down. Oh, and by the way, we have seen yesterday that we can use negative indices in vectors. It's the same thing here. So for example, if I wanted here in IPRG all my observations for all my variables, but the second one, for example, I could use -2, and this would return, it's a little bit too big here to see, but all my variables but the second one. So all the concepts that we have seen yesterday, they apply, they generalize to data frames. The only difference is that we need to use the comma to specify the rows or the columns. Yes?
Just like in the console window, how you do the up arrow and you get things come up. In the script window, you can't do that, right?
No, in the script window, you go up. In the script window, you go up.
Yeah, but there is no shortcut to bring in the command that we typed before it.
No, that only works here. But there is a shortcut. I think it's Control-1 and Control-2. So Control-1, I'm here. If I press Control-2, my cursor is automatically Control. So Control.
Control 2 goes to the console.
Yes, sorry, I was pressing F2. So Control-2 automatically moves my cursor on the console. Control-1 will automatically move it here. So if you're in your script and you're typing something there, you can use Control-2 to move to your console and then start to go on. So an exercise for you here. So 4 questions. So the first one is to create a new data frame called IPRG_200 containing only the information for the 200th observation. Okay. Number 2, notice that if we use nrow, the nrow function can return the number of rows, the number of observations that we have. So you can use nrow to pull out the last information for the last observations that we have. A little bit like we did yesterday for a vector, where we used length. Okay? So try this out, use nrow to pull out the last observation, and play around and use tail and make sure that indeed using tail that gives you the last ones, six last ones by default. make sure that you have the same results. Okay? And then create a new data frame that you would call IPRG last, that contains information for this very last observation. And then create a new data frame called IPRG middle that contains the information for the observation that you find exactly in the middle of your data frame. And finally, using nrow and the minus notation, the minus means everything but these indices, try to replicate the behavior of hat. Hat shows observations from 1 to 6, while try to get the observations 1, 2, 3, 4, 5, 6, but using nrow and minus. Okay, basically everything but those after 1, 2, 3, 4, 5, 6. Okay? So sticky notes down, please, and put your green or blue ones up once you're happy with the exercise you have finished. If anything is unclear, call us and we can work through specific bits. But at the end, we're going to check the exercise, this exercise altogether. So I suggest we, although there are not that many green sticky notes, but from what I have seen, quite a few people have already done most of these exercises, but the last one. Okay? So I suggest we're going to go through everything to 1, 2, and 3 together, and then if you want, you can have a bit more time to do the last one, or we can do it together. So something that I did not mention yesterday is how to, in your R scripts, how to write commands. Okay? And you can write commands with one or multiple hashtags, hash signs. Okay? So I'm going to say here exercise data.frame to somehow have a note in my script that this is the exercise of our data frames. And in general, it's a very good thing to use this to command your scripts. Not to repeat exactly what you do, because the code says what you do, but maybe to define some structure in your scripts, because they tend to become very long, very quickly. So put some structure, or more to define or describe why you do things. Not exactly what you do, because that's what the code says, of course, but why you do things. That's something we tend to find. So the first question was to subset, so what was the first question? IPRG 200, so to subset this big data frame, but only keep the 200th observation and create a new variable IPRG 200. So if I say dim IPRG 200, I get 1 by 7, 1 observation, and all my 7 variables. And of course, the easiest to make sure I get, or at least I don't know if it's really correct, but at least to have something that looks like it's correct, I type the name of the variable, and indeed I have all the information for one variable, and it's supposed to be the 200s. But if this was a more complex calculation, I couldn't have. But we have to live with that. Sometimes we do complex calculations and we get a result that we kind of trust what we did. So the second question was to create IPRG last, which contains the last observation of this data frame. And so how can I do that? Well, if I know that I have 36,321 observation, I could do it like this. Okay. And here is 1 observation, and indeed I get all the variables for 1 observation. It's the this index, but actually I'm not quite sure if that's the last index. It might be if I didn't make a mistake, or maybe it is at this time during our analysis, but maybe we're going to transform the data and suddenly we're going to remove observations, and this line of code would suddenly break because this index doesn't exist, or maybe we have more observations and so we're missing something. So, like we did yesterday with the vector, it's much better to compute this value by using the nrow function. So let's see IPRG last, and indeed it is the same result, but that was nearly one guess. I remember 2021 because I probably said it 10 times by now. But again, this is not a robust program. This would fail as soon as my data fails. And then I could check that this is correct by using the tail function. Manually visualizing or manually checking, is it this protein, is it this intensity, and so on. But that's something we need to accept, that it will not be always possible to kind of look at the results and make sure they are correct. And so the next question was to extract the observation that is exactly in the middle of this data frame. So I can reuse the trick I had before, IPRG, and the one in the middle, well, if I take the number of rows and I divide by 2, I get in the middle. Now, if I divide the number of rows by 2, I don't get an integer, but that's actually fine. I can still use it as it is, IPRG, nrow divided by 2, and R is clever enough to know that if this is an index, it must be an integer, and it's going to do the rounding automatically. But now the rounding happens to be observation 18160. I could use other functions like the ceiling to round upwards, or floor to round downwards, if I was really after an observation in particular.
Is there also any possibility to use like some function like median to extract the middle?
So maybe if we say 1 to nrow IPRG, we create this long vector that starts for 1, and then maybe here if we take the mean, yeah, so the mean of all these is, but it's slightly different. But that would be a slightly convoluted way of. No, it's not too complicated. And the only thing is that we need to realize that if we do it like this, the rounding will give us 18160, and we compute the mean of all these, we get 18161. So slightly different result. It doesn't matter here, but we need to realize that different ways to find a result might lead to different answers, and some might be wrong. And so the last question was, would you like some time for the last question, or should we do it all together? Do you want me to do it? Yeah. Okay. So the idea was to emulate the behavior of hat. So hat prints out the 6 first observations, but using minus and nrow, basically saying hat says print only the 6 first, and what we want is print everything but 7, 8, 9, 10, and so on. Okay. So how do we define 7, 8, 9, 10, and so on up to the very last one? We can use 7, 2. What's the index of the very last one? I don't know, or I don't remember, and I don't want to know. The point is, I don't need to know, because I can calculate it myself. Okay. So this creates now the vector. It's too big to see, but it starts at 7 and finishes at the last index. So if I was to say IPRG and this, I would essentially get the opposite of what I want. I would get all observations, well, no, I would get all but the 6 first, 7, 8, 9, 10, and so on. So it's not quite this factor that I want. Let me show you with head. Head, it starts at 7, and then tail, it finishes at the very end. So it's not quite that what I want. What I want is the following. So yes, from 7 to n row IPRG, but I want minus all this. So this creates first my vector 7, 8, 9, 10, and so on, but now I'll put a minus in front. Minus 7, minus 8, minus 9, and so on. And now this is something that I can use as it is to do my subsetting. And to, at the end, remove everything but 1, 2, 3, 4, 5, 6. Now that's of course a somehow convoluted way to see the 6 first one. But it's a good way to play around with n row, column, 7, and familiarize yourself with different ways of subsetting our observations. So we're going to use data frames much more later, but I want to briefly talk about factors. So here if I type str IPRG, the structure of this data frame, I see that I have some variables like log2 intensity, intensity here, that are numbers. You know, the num stands for numeric, so these are vectors of numbers. But I also see that I have, in some cases, like protein, condition, and so on, something called a factor. And originally these looked like characters, protein identifiers like characters, but are transformed, at least if we use read.csv, it transforms these characters into vectors, into factors. Sorry. And so a factor, and I'm going to create a factor here. So for example, if I have a set of observations, so I'm going to create this as if it was a character. But I'm going to transform this vector of characters into a factor. And a factor is a way to encode, let me store it here, to variable, is a way to encode categorical data. So here we have, in these observations, a male, a female, a male, a female, and it tells me that the levels I have, and I can also use the, which is here, the function levels in this variable sex are either male or female. So the factors store some information about the categories, about all the elements that are to be expected inside this factor. And so my first level is female, and my second level is male. And actually, the way this data is encoded is as 2, 1, 2, 1. Where my first element is of level 2, my second element is of level 1, my third element is of level 2, and my last element is of level 1. So this data structure knows that this and this element are the same because they point to the same level. And the second and the fourth element are also the same because they point to the same level. As opposed to a character, if I only have this character here, although when we look at it, we know that the first and the third one are the same and the second and the fourth one are the same because we look at it. But these are encoded as just strings, that they happen to be the same. Whereas in factors, the fact that we have categories, two possible categories in this case, male and female, and that all the observations are either first level or second level. This is what factors do. Yes? No. So here, the first level is female because F and male is second because of M. It is possible to define the levels, or the order of the levels yourself, by saying levels equals C, and so the first one would be male, for example, second female. And now if we look at sex, the first level is male because that's how we define it. Otherwise it would take automatically the alphanumeric. Yes?
Are the levels case sensitive?
Yes, like everything in R, they are case sensitive, yes. But we could try. If I take the first, I'm going to do it here with this one, capital M, and execute it. See, now suddenly I have three levels. Female, of course, in first in the alphabet, and then lowercase m, capital M. Sorry. Yeah. So yes, it's all case sensitive. So this is actually has major side effects when we read our data in. Because when we create a factor, we kind of define what all these categories are. In this example, I do not expect to find other observations that would be something else than male or female. And this is somehow encoded in the fact that this is a factor like this. Whereas for characters, I just add characters, whether they're the same or different, it doesn't matter for the data structure as it is. So very often, when we read data in, it might be worth thinking whether the data that we have, is it meant to be a factor, or actually it's not meant to be a factor. Typically, if we read the data in and we have these protein identifiers, do we really want these to be factors? Do we kind of define that these are all the possible protein identifiers that we expect to see? So very often what we do, and so I come back here at the very top of my script, okay, what we did here, I'm going to copy this line at the very bottom here. R does this conversion automatically with read.csv. And if we don't want this conversion to be done automatically, we can use an option called strings as factors and set it to false. That means do not automatically convert the strings to factors. So that's factors are really useful in many use cases, but in other use cases they might actually be quite annoying. So it might be a good thing to, the first is to know about this, that there is this conversion that happens or can happen, and then to set it to false to avoid it. And so if I rerun this line of code, and I ask strg, str, the structure of this new iprg, or variable that I overrode, now I can see that my protein is indeed a character, my condition is a character, so now I either have numbers, integers, or floats, or characters. This conversion has not been done automatically. So these are what factors are, and they are often very, very useful, but in some cases, it's not really what we want. But we can do the conversion from one to another. So for example, here I have, let me use the one that is, that has no two factors here. If I have this factor, we can use a function, the function that we have actually seen yesterday as character, and it's going to convert it to characters. So if we happen to have factors, we can always convert this, force them to be characters. And if we have characters, like for example, iprg $protein, this is a character now. If I wanted to make it a factor, I could use the factor or as factor function to convert it into a factor. If I have a character, but I really want to have a factor. But probably in the first approximation, characters will do the job. So that's a rather important argument to read.csv. Let's have a quick look at the documentation of read.csv. So read.csv is actually a family of functions. There is read.csv, there is read.csv2. That's if your separator is a semicolon. We have read.delim if your separator is a tab. Read.delim2 if your separator is a tab, but you use a comma for a decimal separator. And so all these functions are kind of special cases of the most general function, which is read.table. And read.table, you have to set all these parameters yourself manually. So for example, well, the first one, file, is the name of the file that we want to read in. But the second one, header, tells you, is the first line in my CSV file, my TSV file, or my spreadsheet that I want to read in, is it a header? Does it contain, does it encode the names of the columns? So by default for read.csv, it's true. Very often when you have your CSV files, the first rows contain the names. But the default for read.table is false. So if you happen to get a spreadsheet, a text-based spreadsheet, that is not a plain text or plain CSV or TSV and so on, and you need to parameterize the parsing and the reading into of that file, have a look at read.table and all these options, and chances are you'll be able to set them so that you can read your data in directly or nearly directly as setting these options.